Right now, as you're watching this, there's a star dying somewhere in our galaxy. It's not going quietly. It's swelling, expanding, growing so impossibly large that if you could somehow stand on its surface and look out at the horizon, you wouldn't see a curve. You'd see flatness. An endless plane of roiling plasma stretching in every direction, further than entire planets orbit their suns. This thing is so big that our entire solar system, Earth, Mars, Jupiter, Saturn, all of it, would fit comfortably inside, and there'd still be room left over. We live in a universe that builds monsters, titans so vast they make our sun look like a flickering candle in a warehouse. And we're about to meet the biggest one we've ever found. But to understand it, we first need to understand how the universe breaks its own rules. Let's begin. Stand on Earth. Look around. Mountains that took millions of years to form. Oceans that stretch beyond sight. We are, each of us, impossibly small against this backdrop. Our entire lives play out on this spinning ball of rock, and it feels infinite. But let's zoom out. Earth? Just a pale blue dot. One planet among 8. And our sun? Sure, it's big. Tuck over 1 million Earths inside it, and you'd still have room to spare. For us, that's incomprehensible. Divine, even. But here's the thing, and I need you to really hear this. Our sun is pathetically, almost embarrassingly average. A cosmic nobody. A regular yellow dwarf star in a galaxy drowning in hundreds of billions of other stars. Many of them bigger. Some of them so much bigger that the word bigger starts to lose all meaning. The universe doesn't care about what feels big to us. It operates on scales that mock our intuition, that laugh at our sense of proportion. And we're about to climb that ladder. Each rung will redefine everything you thought possible. Ready? Let's start ascending. Every star begins the same way. A cloud of gas and dust collapsing under its own gravity, spinning, heating, compressing. Then, ignition. Nuclear fusion roars to life in the core, and a star is born. But here's where it gets interesting. Not all stars are created equal. Mass is destiny in the stellar world. It's the single factor that determines everything. How bright a star will shine, how hot it will burn, and crucially, how long it will live. Imagine a graph. On one side, temperature. On the other, brightness. Plot every star we've ever observed, and you'll see a pattern emerge. We call it the Hertzsprung-Russell diagram, a cosmic family tree that reveals the secret lives of stars. Small stars? They're the tortoises of the universe. Red dwarfs that burn slow and steady, sipping their fuel over trillions of years. They'll outlive everything. They'll still be burning long after our sun has died, long after humanity is forgotten. But massive stars? They're the shooting stars, the supercars with the gas pedal welded to the floor. They don't sip, they devour. They burn hundreds of thousands of times brighter, running at temperatures that would vaporize anything we can imagine. And here's the cruel irony. The bigger and brighter you are, the faster you die. The universe's most spectacular stars live fast and die young, burning through their fuel in just a few million years, a cosmic eye blink. But before they go out, oh, do they put on a show. Let's talk about mass. Pure, crushing, gravitational mass. For most of cosmic history, scientists believed there was a hard limit. The Eddington limit, a theoretical maximum where a star's radiation pressure becomes so intense that it literally blows itself apart. No star, we thought, could exceed about 150 times the mass of our sun and survive. Then we found R136A1. lurking in the Tarantula Nebula, 160,000 light-years away. This absolute monster weighs in at over 250 solar masses. It shouldn't exist. By all the rules we'd written, it had no right to be there. This is a Wolf-Rayet star, a stellar heavyweight that's already blown off its outer layers, exposing a nuclear inferno underneath. It's bleeding light into space at a rate so extreme that it outshines our Sun by a factor of nearly 9 million. 9 million. If you replaced our Sun with R136A1, Earth wouldn't just be scorched, it would be instantly vaporized. The inner solar system would become a pressure cooker of radiation so intense that even the rocky planets would start to evaporate. But here's the thing. R136A1 is massive, incredibly dense, impossibly bright, but it's not actually that large. Pack all that mass into a relatively compact space, and yeah, you get mind-bending density, but not mind-bending size. For size, true, incomprehensible scale, we need to look at stars that have reached the end of their journey. Stars that have swollen to proportions that beggar belief. Every massive star follows the same path. Burn through your hydrogen. Start fusing helium. Then carbon. Then neon. Oxygen. Silicon. Each stage shorter than the last. Each burning hotter until you can't go any further. And then something extraordinary happens. The core contracts. But the outer layers? They expand. They swell. They balloon outward at scales that would make our Sun look like a period at the end of a sentence. Welcome to the realm of the red supergiants. You know one already. Betelgeuse. That reddish star in Orion's shoulder that's visible to the naked eye from your backyard. Seems normal enough, right? If you put Betelgeuse where our Sun is, its surface would stretch past Mars. Mercury, Venus, Earth, Mars, all of them would be inside the star, orbiting within the outer atmosphere of a dying giant. And Betelgeuse isn't even close to the biggest. These stars have burned so bright, lived so hard, that they've exhausted their options. Their cores are collapsing, but their outer shells are expanding in a last, desperate gasp for existence. They've become bloated, cool, impossibly vast. They're dying, but what a way to go. Now we arrive at the summit, the absolute peak of stellar enormity, UY Scuti. Say that name slowly. Let it settle, because what you're about to hear will break your brain. UY Scuti is a red supergiant located about 9,500 light-years away in the constellation Scutum. It's flickering, unstable, oscillating in size as it struggles against its own impending death. At its largest, this star has a radius over 1,700 times that of our Sun. Stop. Let that sink in. Not 17 times, not 170 times, over 1,700 times. If you placed UY Scuti at the center of our solar system, its surface would extend beyond the orbit of Jupiter. Saturn might just barely escape, sitting right at the edge of this stellar colossus. You could fit approximately 5 billion suns inside UY Scuti. 5 billion. Light traveling at 300,000 kilometers per second would take over 7 hours just to make one lap around this thing. Our Sun? Light circles it in under 15 seconds. Standing on a planet near UY Scuti wouldn't give you a view of a star. You'd see a wall, an endless glowing horizon that fills your entire sky. The very concept of star breaks down. It's not a point of light anymore. It's a presence, a God made manifest. This is what the universe builds when it decides to show off, when it takes the same basic ingredients, hydrogen, helium, gravity, and asks, how far can we push this? From our tiny Sun to the incomprehensible vastness of UY Scuti, We've climbed the cosmic ladder. We've seen stellar behemoths that dwarf our imagination, that redefine what large even means. And here's the final twist. UY Scuti won't last. None of these giants will. They're all dying. In cosmic terms, they're already gone. Supernovae waiting to happen. Black holes in the making. But for now, for this brief moment in the universe's 13.8 billion year story, they exist. Burning, shining, reminding us just how small we really are, and how magnificent existence can be when you know where to look.